Welcome to G-Fun Facts Online. Today we are looking at the ocean not just as a body of water, but as a chaotic, relentless force. It is a dynamic environment where millions of tons of steel are expected not just to float, but to remain upright against wind, waves, and the shifting weights of cargo and passengers. When you see a cruise ship like the Icon of the Seas, which stands 20 decks high and looks top-heavy enough to topple in a stiff breeze, yet cuts through a hurricane with wine glasses barely trembling on dinner tables, you are not witnessing magic. You are witnessing a triumph of physics, engineering, and centuries of hard-learned lessons written in blood and salt water. This episode is the story of that invisible battle between gravity and buoyancy. It is a deep dive into the mathematics of survival, the engineering of comfort, and the tragic history of what happens when we get it wrong. To understand how a ship stays upright, we must first understand why it floats at all. It begins with a principle discovered in a bathtub more than 2,000 years ago. Archimedes' Principle is the bedrock of naval architecture. It states that an object immersed in a fluid is buoyed up by a force equal to the weight of the fluid it displaces. A ship weighing 100,000 tons must displace 100,000 tons of water to float. If it displaces less, it sinks. This is why steel, which is far denser than water, can float. The hull is shaped to enclose a massive volume of air, making the average density of the ship less than that of the ocean. But floating is the easy part. A log floats, but it rolls freely in the water. A ship must float upright. This requirement introduces us to the most critical points in naval architecture, a set of letters that every deck officer memorizes: K, B, G, and M. Let's break these down. K is the keel, the baseline reference point at the very bottom of the ship. B is the center of buoyancy. This is the geometric center of the underwater hull volume. This is where the upward force of the water acts. You can imagine the ocean pushing up on the ship through this single point. Then we have G, the center of gravity. This is the geometric center of all weights on the ship, including the steel, the cargo, the fuel, the passengers, and the engines. Gravity pulls the ship down through this single point. Finally, there is M, the metacenter. This is a theoretical point that determines stability. When a ship heels or tilts, the shape of the underwater hull changes. The center of buoyancy shifts toward the lower side. If you draw a vertical line up from the new position of the center of buoyancy, it intersects the ship's center line at point M. The relationship between the center of gravity, G, and the metacenter, M, is the single most important factor in a ship's initial stability. The distance between them is called the metacentric height, or GM. If M is above G, we have stable equilibrium. When wind pushes the ship over, the upward force of buoyancy moves outboard of the downward force of gravity. This creates a righting lever that twists the ship back upright. However, if G is above M, the ship is unstable. When it heels, the force of gravity pulls the high side down further, and the force of buoyancy pushes the low side up, flipping the vessel. This is often the cause of capsizing. There is also a state called neutral equilibrium, or 0 GM, where G and M are at the same point. The ship has no tendency to right itself or capsize. If you push it to 10 degrees, it stays at 10 degrees. This is affectionately known as a floppy ship. The magnitude of the GM determines the ship's personality. A stiff ship has a large GM and a low center of gravity. It is very stable and resists heeling. However, when it does roll, it snaps back to upright violently. This is great for safety but terrible for comfort. On a stiff ship, you might not capsize, but you might break a leg or get violently seasick due to the rapid, jerky motion. On the other hand, a tender ship has a small GM and a higher center of gravity. It rolls slowly and deeply. It feels lazy in the water. While comfortable for passengers because the accelerations are lower, a tender ship is closer to the danger zone. If the GM gets too small, a strong wind or a sharp turn could push it past the point of no return. Even a perfectly designed ship faces dynamic threats that can destroy its stability in seconds. One of the biggest enemies is the free surface effect, often called the silent killer. Liquids on a ship such as fuel, fresh water, and ballast are rarely frozen in place. They slosh. Imagine a wide, shallow tank half full of water. As the ship heels to the right, all that water rushes to the right side of the tank. This shift in weight moves the ship's overall center of gravity toward the heel, reducing the righting lever. Effectively, the free surface effect makes the ship feel like its center of gravity is higher than it actually is. This effect is proportional to the cube of the tank's width. A tank that is twice as wide is 8 times more dangerous. This is why ship designers use longitudinal bulkheads to divide wide tanks into narrower ones, breaking the sloshing momentum. Another critical concept is the angle of yaw. If a ship has a negative GM and is unstable upright, it won't necessarily capsize immediately. It might flop over to an angle, say 15 degrees, where the hull shape changes enough that the center of buoyancy moves far enough out to finally create a positive righting arm. The ship then hangs there, listing at 15 degrees. This is the angle of yaw. It is a terrifying condition. If a captain sees their ship listing, their instinct might be to fill a ballast tank on the high side to correct it. But if the ship is in a lull, adding weight high up might reduce stability further, causing the ship to violently flop to the other side and capsize. The correct procedure is often to fill tanks on the low side first to lower the center of gravity, a counterintuitive move that requires nerves of steel. Then there is parametric rolling. This is a modern phenomenon, particularly dangerous for container ships with flared bows. It occurs when the ship's length matches the wavelength of the sea. As a wave crest passes amidships, the ship's waterplane area decreases because the bow and stern are hanging in the air. This reduces stability. When the wave trough is amidships, the bow and stern dig in, the waterplane area increases, and stability spikes. If this cycle of stability rising and falling matches the ship's natural roll period, it creates a resonance. Like a child pumping a swing, the roll gets bigger with every wave. A ship can go from calm to rolling 40 degrees in just a few cycles, snapping container lashings and sending cargo overboard. The rules of stability were not derived in a classroom. They were written in the wake of disasters. Let's look at a few historical case studies. In 1628, the Swedish warship Vasa sank on her maiden voyage due to the king's vanity. The Vasa was meant to be the most powerful warship of her time, carrying 64 bronze cannons. But King Gustavus Adolphus constantly changed the requirements, demanding more guns and a second gun deck. The shipwrights, afraid to defy the king, built a superstructure that was too tall and heavy for the hull's width. Before sailing, the captain performed a stability test where 30 men ran back and forth across the deck. The ship rolled so violently the test was stopped to prevent her from capsizing at the dock. They sailed anyway. Less than a mile into her maiden voyage, a light breeze caught her sails. She heeled over, the lower gun ports dipped below the waterline, and she sank in minutes. The lesson here is form stability. The hull must be wide enough to support the weight above it. In 1915, the SS Eastland disaster showed us the tragedy of good intentions. After the Titanic sank, the US government required lifeboats for all passengers. The SS Eastland, a Great Lakes steamer known for being tender, was retrofitted with heavy lifeboats on her upper decks. While tied to a dock in Chicago, the extra weight of the lifeboats, combined with a crowd of passengers moving to one side, raised the center of gravity critically high. The ship rolled over at the dock, killing 844 people. The lesson is that modifications matter. You cannot simply add safety gear without recalculating stability. In 1987, the Herald of Free Enterprise capsize taught us about the dangers of open decks. RORO ferries have large, open vehicle decks that must remain free of bulkheads. The Herald left Zeebrugge with her bow doors open due to negligence. Water washed onto the vehicle deck, surged to one side, and the ship turned over in 90 seconds. This led to the Stockholm Agreement and new regulations for ferry stability. More recently, in 2006, the Cougar Ace incident highlighted operational sequence. This massive car carrier began draining ballast tanks to refill them with fresh ocean water to prevent invasive species transfer. The crew drained the starboard tanks while the port tanks were also slack, creating a massive synchronized free surface effect. The ship instantly heeled 60 degrees. She didn't sink, but she floated on her side for weeks. Modern loading computers now simulate ballast exchange steps to prevent this. So how do we tame the roll? Naval architects have developed an arsenal of technologies. First, we have bilge keels, the passive defenders. These are long metal fins, running along the turn of the bilge underwater. As the ship rolls, the flat surface drags against the water, creating turbulence and dampening the motion. Then there are anti-roll tanks, which fight water with water. These are U-shaped tanks tuned so that water flows from side to side out of phase with the ship's roll. When the ship rolls to port, the water is still rushing to starboard, pushing the ship back down. For cruise ships, the gold standard is active fin stabilizers. These are movable metal wings that extend from the hull. They work like airplane ailerons. If the ship rolls to starboard, the starboard fin tilts up to create lift, and the port fin tilts down to create downforce. Modern fins are gyro-controlled and can reduce roll by 90%. Some are even designed to flap like fish fins to stabilize a yacht at anchor. We also use gyro stabilizers, which utilize a heavy flywheel spinning at high speed inside a vacuum sphere. When the ship tries to roll, the gyroscope tilts, and hydraulic cylinders fight this tilt, exerting a massive torque back on the hull to lock it in place. A newer technology is Magnus effect rotors, where spinning cylinders extend from the hull to create lift, similar to how a curveball curves. Now, let's talk about the modern Titans. When people see the icon of the seas, a 250,000 gross ton behemoth, they ask how it doesn't tip over. It looks like a skyscraper on a barge. The answer lies in density distribution and beam width. First, the iceberg principle applies. While the superstructure is huge, it is mostly air. The cabins and dining halls are vast open spaces made of lighter steel or aluminum. In contrast, the bottom of the ship is dense, holding massive engines, fuel tanks, and water supplies. This keeps the center of gravity surprisingly low. Second, the extreme beam width helps. The icon of the seas is roughly 65 meters wide. Stability is heavily influenced by the width of the ship. A ship that is 10% wider is roughly 33% more stable. Finally, the use of AZI pods instead of rudders allows for a boxier hull form, maximizing buoyancy distribution at the edges. Stability isn't just about survival, it's also about not ruining the buffet. Naval architects use ISO 263-1-1 to quantify human exposure to motion. The human ear's vestibular system is sensitive to vertical accelerations. To minimize motion sickness incidents, or MSI, designers face a comfort paradox. To make a ship safe, you want a stiff ship with a large GM, but a stiff ship snaps back quickly, causing sickness. To solve this, designers aim for a tender ship with low accelerations and use active stabilizers to prevent dangerous roll angles. On the operational side, every modern cargo ship has a chief officer who uses a loadicator computer. Before a single container is loaded, the cargo plan is input into this software to calculate draft, trim, intact stability, and shear force. Despite the digital tools, the ultimate check is the draft survey. In port, an officer visually reads the draft marks on the hull and calculates the ship's displacement by hand, a ritual connecting the digital age to the days of sail. Looking to the future, we are moving toward the autonomous captain. Companies are developing AI routing that uses LiDAR and wave radar to map the sea state miles ahead, adjusting course to avoid parametric rolling resonance. Auto-ballasting systems will dynamically pump water to counteract wind gusts. And regulations like safe return to port ensure that even after a fire or flooding, a passenger ship can act as its own lifeboat. A ship is a bubble of air and steel suspended between two fluids, the water below and the wind above. Its survival depends on the center of buoyancy, always outmaneuvering the center of gravity. From the wooden ribs of the Vasa to the computerized fins of the icon of the seas, the history of ship stability is a history of humanity trying to impose order on chaos. We have learned that you cannot cheat physics. You can only negotiate with it, using geometry, mass, and the eternal vigilance of the men and women who watch the inclinometer, waiting for the sea to make its move. Thanks for listening to G Fun Facts Online.